Hello, good morning. My name is Nikos Mastorakis. Together we will have the course Nonlinear Systems and Neural Networks. With me, you will have the first part of the Nonlinear Systems. For our course of nonlinear systems and nonlinear systems and neural networks. For the part of nonlinear systems, we will use this book that I sent you last night by email. I sent you this book in PDF, Applied Nonlinear Control. It's a classical book by the authors Zlotin Lee, Jean-Jacques Zlotin and Whipping Lee. So from this book, these are professors, as you can see, in Massachusetts Institute of Technology, known as MIT. We will study from this book the first 200 pages. It's a very big book, but we will study the first 200 pages. These are the contents of the book. And we will study the introduction, the first chapter, the second chapter, phase plane analysis, together. The third chapter is about fundamentals of Lyapunov theory. The fourth chapter, until this page. Practically the first 5 chapters is our part of our course of nonlinear systems. So, why nonlinear systems are so important? Nonlinear systems are very important because in nature and in technology, only some very small devices like a resistance or like a spring have linear behavior. All the other systems, very big systems like biological systems, complicated technological systems, other systems in nature are nonlinear systems. What does it mean that a system is nonlinear? A system is nonlinear if we don't have the concept of linearity. What does it mean, linearity? Linearity means that if you have input A, for input A, you have input B. In a linear system, if you multiply the input A by 3, the output B must also be multiplied by 3. So, for a linear system, an input A gives output B. 10 times A must give 10 times B in linear systems. In nonlinear systems are systems that you don't have this concept. You don't have this. So in nature, almost all the systems are nonlinear, but in many times we linearize them, we approximate them with linear models around some area or around their equilibrium point. So the main concept, the main idea here is that all the systems in nature are nonlinear systems. The linear systems are exemptions of the rule. So a linear system is a very simple system, and that you can describe it with some simple algebraic or differential equation, always linear. So linear systems are described by linear algebraic or linear differential equations. But this is only a small minority of the systems. The vast majority of the systems are the nonlinear systems. Humans, animals, all the biological organisms are nonlinear systems. The economy of our country is a non-linear system. All the other systems are non-linear, and non-linear systems are described by difficult mathematics. In sometimes we can describe them by non-linear differential equations. Nonlinear systems, a system, as engineers, we describe a nonlinear system by nonlinear differential equations. Many times we must control the systems, and for this system, we must examine the nonlinear control of the system. So let's see what is the mathematical background of this course. The mathematical background of this course are the mathematics that you have studied in the first 2 years in the Technical University of Sofia. So you must make a reiteration, a repetition of standard mathematics, calculus of one variable, calculus of multiple variables, and of course differential equations. Also, an introduction to automatic control systems theory is necessary in order to understand this course. Without automatic control, you cannot understand this course, of course, and this will be a problem. So if you want, please go back and make a repetition for automatic control, for control systems, and this reiteration of control systems theory will be very useful in our nonlinear systems course. So, for example, you must recall from control systems what is Laplace transform, differential equations, state space model like this in equation 1.2. All these things are very useful from automatic control, and you must recall them. Okay. Let's see for example here as a first example of a nonlinear system. A simplified model of a nonlinear system is this. The model of the motion of an underwater vehicle. This equation here in your book is the equation 1.3, describes the motion of an underwater vehicle. So we must see this equation that you have here. We have here this differential equation. Okay, v is the velocity, dot v is the derivative, and u is the external force in our underwater vehicle. So this is a differential equation, but it is not linear. It is a nonlinear differential equation. This is why our system is nonlinear, because our system is described by a nonlinear differential equation. dv or derivative of v with respect time plus v multiplied by absolute value of v equal to u. This term makes the system nonlinear. This term makes the system as nonlinear. So let's say, for example, that for this system, we apply a step function as input. So u for this system, u is 0, z is 1, u, which is the thrust, is 1 from 0 to 5. From 0 to 5 seconds is 1 and then is 0. If we solve this differential equation, we will find that the velocity is has this curve. The velocity has this curve, and if we apply how we can solve this? This is very easy to solve, because if you apply this, if you put here the absolute value, in the first case you put the absolute value without absolute value, and if you solve this equation easily, then you have this as velocity here. Okay, in your book you can see how we have this solution. So this is a nonlinear system. Why this is a nonlinear system? Look what is very nice here. You have this input with amplitude 1, and this is the output. If we multiply this by 10, then for linear systems, simply the output must be multiplied by 10. In nonlinear systems, this is not true. In nonlinear system, this input is 10 times this input. This input is 10 times this input. The second input here, 10, is 10 times than this input. But this output is not 10 times of this output. On the contrary, this output is smaller. So this is why this system is nonlinear. Here you have input with amplitude 1, and this input gives this output. Here this gives by 10, is multiplied by 10, and this that it's multiplied by 10 gives this with smaller amplitude. Okay, and this is why our system is nonlinear. Some common nonlinear systems behaviors. Let us now discuss some common nonlinear system properties, so as to familiarize ourselves with a complex behavior of nonlinear systems and provide a useful background for our study in the rest of this course. Let's see, for example, so the first thing that we have seen here is that if you have a system and this system is multiplied, the input of your system is multiplied by a factor, it is not necessary that the output is multiplied by the same factor. So this system from 1, this input from 1 is multiplied 10 times and have this, but this output is not multiplied by 10. On the contrary, this output is now smaller. So we have another interesting result here in nonlinear systems is that you can have multiple equilibrium points. What does it mean, multiple equilibrium points? You know very well that in linear systems you have only one equilibrium point. Only one equilibrium point is the equilibrium point. What does it mean, equilibrium point? Equilibrium point means where all the parameters of the state space vector are 0. Here the equilibrium point, excuse me, not exactly this. Equilibrium point means dx1 is equal to 0, dx2 equal to 0, dxn equal to 0. All the derivatives are equal to 0 of the state space vector. So in a linear system you have one equilibrium point, but for non-linear systems you can have multiple equilibrium points. How we can see this? Let's see a simple example. Consider, for example, the first order system x dot equal minus x plus x square with initial condition x0 equal to x0. This linearization, the linearization of these systems, make x dot equal minus x plus x square. This linearization is x dot minus x. What does it mean? Its linearization is this. Means that for small x, you have here x dot equal minus x plus x square. For x equal to 0, everything is 0 here, and x equal to 0 is equilibrium point. because for x equal to 0, you have dx dt equal to 0. What does it mean, linearization? Linearization means that around the equilibrium point, your system has behavior as linear system. So very near to equilibrium point, you have x dot equal minus x. Why? Because x square is very small, is negligible, and you can omit, you cannot take into account the x square, because x square is very smaller if you compare it with x. So around the equilibrium point, x dot is equal minus x. So the solution of this linear equation now is this, the solution, without the term x square, because we have made linearization around the equilibrium point. And if you see, around the equilibrium point, you can it is plotted in 1, 3, A. Where is 1, 3A? 1, 3A is this figure, the behavior of your system. So you see x, you have this, x tends to 0. Okay. Now you can see that you can, another equilibrium point is the point 1. Why? You have equilibrium point, the point 1, because if you put as x 1, 1 and 1, x dot equal to 0. So x dot equal to 0 means you have another equilibrium point. So when the derivative of the state space vector is 0, you have equilibrium point. Dx dt equal to 0, that means you have an equilibrium point. For first order systems, we can understand what is equilibrium point if we solve the equation x dot equal to 0. So for this simple system, the points 0 and 1 are equilibrium points. Why are these points equilibrium points? Because for x equal to 0, but also for x equal to 1, x dot is equal to 0. X dot is equal to 0 means that if you go to the equilibrium point, you will stay in the equilibrium point. But if the equilibrium point is stable, if you go a bit away from the equilibrium point, you must come back to the equilibrium point. If your system, if the equilibrium point is unstable, then if you go away from the equilibrium point, then you will not go back to the equilibrium point. This is for the other equilibrium point here. So for the other equilibrium point here, you have, for example, this behavior, x dot, xt. So this equilibrium point, the other equilibrium point is unstable. So the system has two equilibrium points, and its qualitative behavior strongly depends on its initial condition. The issue of motion stability can also be discussed with the aid of the above example. For the linearized system, stability is seen by noting that for any initial condition, the motion always converges to the equilibrium point x is equal to 0. However, consider now the actual nonlinear system. While motion started with x0 smaller than 1 will indeed converge to the equilibrium point, those starting with x0 bigger than 1 will go to infinite. In the presence of a bounded external input, stability may also be dependent on the input value. The input dependence is highlighted by the so-called bilinear system. You have this bilinear system. If the input u is chosen to be -1, then the state x converges to 0. If u is equal to 1, then absolute value x tends to infinity. So here, an important thing is that initial conditions plays an important role in the stability of a nonlinear system. Another important thing in nonlinear systems is the concept of limit cycles. We have limit cycles here, while we don't have this phenomenon in linear systems. In nonlinear systems, we have the phenomenon of limit cycles. Nonlinear systems can display oscillations of fixed amplitude and fixed period without external excitation. These oscillations are called limit cycles or self-excited oscillations. This important phenomenon can be simply illustrated by a famous oscillator dynamics introduced by van der Pol. So van der Pol equation describes this second order dynamic system. In a second order dynamic system that it is described by van der Pol equation, we have some interesting phenomena. Interesting phenomena means that here you have limit cycles. Limit cycle means that a system is in a trap. It is something like a trap. Your system goes to a circle and then remains forever in this circle. Well, of course, and sometimes it can be your systems can escape for this kind of trap. This is what we call limit cycles. Bifurcations. As the parameters of nonlinear dynamic systems are changed, the stability of the equilibrium point can change, and so can the number of equilibrium points. Values of these parameters at which the qualitative nature of the system motion change are known as critical or bifurcations values. And here we have an example. This example is the famous Duffin equation. The Duffin equation is described by x dot plus ax plus x3. The damped Duffin equation, which may represent a mass damper spring system with a hardening spring. We can plot the equilibrium points as a function of the parameter A, alpha. Alpha varies from positive to negative, and one equilibrium point split into 3 points. Okay, these things is difficult. It is a bit difficult to understand this mathematics now. We will check it later in this course, and at the moment it is not important to insist here. It is not important to insist here. Chaos. For stable linear systems, small differences, this is very important. For stable linear systems, small differences in initial conditions can only cause small differences in output. Okay? For stable linear systems, small differences in initial conditions can only cause small differences in output. On the contrary, for nonlinear systems, we have the phenomenon chaos, from the Greek word chaos. That means that it depends in the nature of nonlinear systems. Some small differences in the input can create very big dramatic differences in the output, and this can generate chaos. Chaos must be distinguished from random motion. In random motion, the system model or input contain uncertainty, and as a result, the time variation of the output cannot be predicted exactly. Only statistical measures are available. So the random systems, the probabilistic systems, you cannot predict. In chaotic motion, you are in a deterministic problem. Your problem is deterministic, but you cannot describe it with mathematics. So you know exactly the solution. So the solution is always the same. For example, this nonlinear system appears house, and for example, in the 100 second, you can have certain value, always the same value. It is not probabilistic, but it is very, very difficult to be described by simple mathematics. So this, for example, this is the output in these systems. Okay, you cannot describe with simple mathematics this curve. This curve is not described by simple mathematics. And this is the chaotic behavior of a nonlinear system. Chaotic phenomena can be observed in many physical systems. The most commonly seen physical problem is turbulence in fluid mechanics, such as the surge of our in-case stick. Atmospheric dynamics is also another chaotic phenomenon, and also the motion of blood in the human body. In this course, as you can see in this course, we have a lot of phenomena, new phenomena that do not exist in nonlinear systems. In linear systems. In nonlinear systems, new mathematical phenomena appear that you have never heard, you have never obtained, you have never observed in linear systems. Let's make a small repetition. The first is that this. The first is this. That means that if you multiply the input with a constant, so you have 1 gives this. You multiply this by 10, but this is not multiplied by 10. On the contrary, this decreases. Second, you can have multiple equilibrium points. Other problem, your equilibrium point is dependent on the initial conditions. You can have many equilibrium points. One equilibrium point can be stable, the other can be unstable, and not only that, but initial conditions determine if your equilibrium point is stable or unstable. Other phenomenon here are the limit cycles. You can see that a limit cycle is a kind of trap, and your system can be trapped in a limit cycle. An example here in the van der Waals oscillation. Other is bifurcations. What are bifurcations? Bifurcation, as the parameters of nonlinear dynamic systems are changed, the stability of the equilibrium point can also change. So you change the parameters of the system and you change the equilibrium. The equilibrium point can be stable or unstable. This is called bifurcations. Also, chaos. What does it mean, chaos? Chaos means that small differences in the input or in the initial conditions have as a result huge differences in the output. So totally the output of your system can be described by a deterministic equation, but very complicated, and you cannot describe it with simple mathematics. Imagine, for example, a system with this curve here. Look now what is interesting here. If you have here x dot derivative equal to 3, okay, x dot, in another system you have the same parameters, but in another system x dot 0 is 3.0 to 1. Very small difference, And now let's see the output of these two systems. The output of those two systems for the first 22 seconds is absolutely the same. After the 25 second, the outputs are different. This is what we call chaos. Small differences in the initial conditions creates huge differences in the output. So we have many phenomena here, and we must examine them with details. So for nonlinear system analysis here, we start with the so-called phase plane analysis. I have also here some transparencies. The same things, I have them in transparencies, but from the book, in the book always in the book you have more information. I can give you also these transparencies. Actually, these transparencies are based in the book that I show you. Okay. And now, let's go to the chapter 2. The chapter 2, we will examine the phase portraits. What does it mean, phase portrait? Phase portrait means that you have this system, this equation, x1 dot equal f1 x1 x2, x2 dot equal to f2 x1 x2, and you must eliminate time. We eliminate time from these two equations, and we take the so-called phase portrait. Okay, so for example, for this spring, you can take the phase portrait of this. I think it's better. Okay, we will continue with the transparencies, and later we can I can show you again the book. So let's continue with the transparencies here. With the transparencies here. Phase portraits. The phase plane method is concerned with the graphical study of second-order autonomous systems. This is phase portraits. Phase portraits of a mass spring system. The governing equation of the mass spring system is this, and if you put here x, this is the spring, okay? If you put here x t is equal x0 cosinus t and xt equal x0 sinus t, you can have this. Okay, I prefer, okay, this is where my transparencies, I will give you this also. I will give you also the transparencies. I will send you by email, but I think that here it is better now. It is better now to continue with our book. We continue with our book. This is our book, because our book has much more information. Opa. And we finish chapter 1, and we are ready now to study chapter 2. For chapter 2, we go directly to the phase portrait analysis. What does it mean, phase portrait? Phase portrait means that let's start with a system of two variables, x1 and x2, nonlinear system of two variables. This nonlinear system of two variables is described by these two differential equations. You have here these two differential equations where x1 and x2 are the states of the system. I told you to make a repetition in the control systems theory. x1 and x2 are the states of the system, and f1 and f2 are nonlinear functions of the states. Geometrically, the state space of this system is a plane having x1 and x2 as coordinates. We will call this plane as phase plane. Given a set of initial conditions, one minute. Given a set of initial conditions, equations 2.1 defines a solution xt. With time t varied from 0 to infinite, the solution xt can be represented geometrically as a curve in the phase plane. Such a curve is called a phase plane trajectory. So here we must eliminate time. We have the differential equations where these differential equations are non-linear differential equations. This is why I write here F1 and F2. So here you have these non-linear differential equations and you must eliminate time. If you eliminate time from these non-linear differential equations, then you take curves. Such a curve is called trajectory, phase plane trajectory. We will see an example. With the governing equation of the mass spring system of the figure 2.1a, where is the 2.1a? 2.1a is this. This is a system from simple physics, from mechanics, and spring and a mass. If you apply the Newton law, you can find very easily with spring constant equal to 1 that in general the spring constant is k. So the equation is mx dot plus kx is equal to 0. I repeat, m, where m is mass, x second derivative, plus kx, where k is the constant of the spring, the hardening, kx is equal to 0. If for simplicity we put m equal to 1 and k equal to 1, then your differential equation is x double dot plus x equal to 0. Assume now that the mass is initially at rest. Okay, equilibrium. At length x0. The length x0 means our 0 point here, okay? So from physics or from simple mathematics, you know very well that you have an harmonic motion. So xt equal x0 cosinus t, right? X dot, if you apply very simple mathematics, very simple algebraic manipulation, x dot equal minus x0 sinus t, because the derivative of cosinus is minus sinus. So how we can eliminate time? We apply Pythagorean theorem, and if you apply the Pythagorean theorem, you can see x dot plus x square plus x dot derivative square equal x0. That means that you take these trajectories. You have a phase portrait. Phase portrait is a Cartesian plane, and one axis is x and the other axis is x dot. Now you have two state variables, only two state variables. Here in these simple examples, one state variable is the distance and the other state variable is the velocity. The power of the phase portrait lies in the fact that once the phase portrait of a system is obtained, the nature of the system response corresponding to various initial conditions is directly displayed on the phase plane. In the above example, we easily see that the system trajectories neither converge to the origin nor diverge to infinite. So this trajectory, no trajectory goes to 0 and no trajectory goes to infinite. A major class of second-order systems can be described by differential equations like this. In state space form, this dynamic can represent it as x1 dot equal to x2, x dot is equal to this. Okay. 1 minute to explain this. In general, for second-order systems, what does it mean, second-order system? Second-order system is a system where you have second derivative. First derivative, your variable x, the first derivative and the second derivative. So the major class of second-order systems can be described by this. We define x1, the x is defined as x1 here. The x is defined as x1, and as x2 is defined x dot. We will not use x3. For second order systems, we will use only x1 and x2. x1 is the x and x2 is the derivative of x. Most second order systems in practice, such as mass damper spring system in mechanics or resistor coil capacitor systems in electrical engineering, can be represented or can be transformed into this form. So in mechanics, you have mass, damper, and spring. Mass and spring. We see here mass and spring. Damper is, damper is when you have damping, okay, in mechanics. So, or in electrical engineering, resistor is the resistance, the electric resistance, coil, and capacitor. These systems can be typically described by equations like 2.3. For these systems, the states are x and the derivative x dot. Traditionally, the phase plane method is developed for the dynamics 2.3, and the phase plane is defined as the plane having x and as x dot coordinates. But it causes no difficulty to extend this method to more general systems. With more variables. So here we will start our analysis. We will start our analysis only for second order systems. For second order systems means that you have two variables, two states space variables for second order system. In a third order system, you will need 3 variables. In a fourth order system, you will need 4 variables. In a fifth order system, you will need 5 variables. Okay, so for second order systems like this, you will need only 2 variables, x1 equal to x and x2 equal to x dot. Singular points now. An important concept in phase place analysis is that of singular point. A singular point is an equilibrium point in the phase planes. Since an equilibrium point is defined as a point where the systems can stay forever. The system can stay forever if x dot is equal to 0. The values of the equilibrium states can be solved from 2.4. So let's see what we have here. You have here, this is your the system of your equations. The system of your equation is this. Okay. Equilibrium singular points are points where x1 dot equal to 0 and x dot is equal to 0, x1 dot is 0 and x2 equal to 0. So singular points here are also called as equilibrium points. Okay, equilibrium points. So let's see a first order system. Let's see a first order system. A first order system is this. How many equilibrium points you have here? How many equilibrium points you have here? You must solve this equation. Minus 4x plus x3 equal to 0. If you solve this algebraic equation, you find 3 equilibrium points. Okay? So singular points are the equilibrium points, the same thing. So here you have 3 equilibrium points. Let's depict these equilibrium points in the face let's depict these equilibrium points in our face portrait. Let's depict these equilibrium points in our face portrait. If we depict these equilibrium points to our face portrait, that means a Cartesian product with x and x dot, then you see that you have 3 points. This in -2, this in 2, and this in 0. You can see that this point is unstable, this point is unstable, and this point is also stable. Symmetry in phase. The stability, we will examine the stability later, not now, but it is something that we will see later. Symmetry in phase plane portraits. A phase portrait may have a priori known symmetry properties which can simplify its generation and study. If a phase portrait is symmetric with respect to x1 and x2 axis, one only needs in practice to study half of it. If a phase portrait is symmetric with respect to both the x1 and x2 axis, only 1/4 of it has to be explicitly considered. Before generating a phase portrait itself, we can determine its symmetry properties by examining the system equations. Let us consider the second order dynamics of the equation 2.3. The slope of these trajectories can be found by this mathematical formula. Why we have this? We go back here. dx1 dt, dx2 dt, and we divide these equations, and from this we take this, and as slope you can find this. Symmetry about the x1 axis. The condition of symmetry about the x1 axis is this, while the condition for symmetry about the x2 axis is this. We can have also symmetry about the origin in the phase portrait. For the symmetry about the origin in the phase portrait, we have this. How we can construct now a phase portrait? Today, phase portraits are routinely computer generated. In fact, it is largely the advent of the computer in the early 60s and the associated ease of quickly generated phase portrait, which spurred many advances in the study of complex nonlinear dynamic behaviors such as house. However, of course, it is still practically useful to learn how to roughly sketch phase portraits or quickly verify the possibility of computer outputs. So we can have the analytical method, and there are 2 techniques for generating phase plane portraits analytically. Both techniques lead to a functional relations between the 2 phase variables x1 and x2 in the form 2.6 g x1 x2 c equal to 0, where the constant c represents the effects of initial conditions and possibly of external input signals. Plotting this relation in the phase plane of different initial conditions yields a phase portrait. The first technique involves solving the equations 2.1 for x1 and x2 as function of time. So from here you have x1 equal g1t, x2 equal do t, and then eliminating time t from these equations, leading to a functional relation in the form of 2.6 of this equation. This technique was already illustrated in the previous example. The second technique involves directly eliminating the time here and then solving this equation of a functional relation between x1 and x2. Let's use this technique to solve the mass spring equation. By noting x dot equal to this, we can rewrite 2 as follows. Integration, if you integrate this equation, then this integration of this equation yields this. One sees that the second technique is more straightforward in generating the equations for the phase plane trajectories. Most nonlinear systems cannot be easily solved by either of the two aforementioned techniques. However, for piecewise linear system, an important class of nonlinear systems, this method can be conveniently used as the following example shows. You can study this example. I leave it to you as homework. And then we must introduce the method of isoclines. The basic idea of the method of isocline is this. You consider isoclines with slope alpha, dx2, dx1 equal to f2 x1 x2 over f1 x and 2. And then you determine alpha as a constant number, and you solve, instead of solving difficult differential equations, you must solve this algebraic equation. And then you must draw in the phase portrait the isoclines. Connecting now the various isoclines, you can have the trajectories of your system as this figure shows. Along the line, we can draw a lot of short line segments with slope alpha. By taking alpha to be different values, a set of isoclines can be drawn, and the field of directions of tangents to trajectories are generated as shown in figure 2.7. To obtain trajectories from the field of directions, we assume that the tangent slopes are locally constant. Therefore, a trajectory starting from any point in the plane can be found by connecting a sequence of line segments. Let us use now the method of isoclines to study the van der Pol equation. If you use the van der Pol equation, which is this, then you can take various isoclines. Look, one isocline is this, isocline, and then you take the slopes. This is a slope, this is another slope, this is another slope. You connect these slopes and you take the trajectories. So isoclines are these curves and trajectories are these curves. Determining time from phase portraits. Note that time does not explicitly appear in the phase plane having x1 and x2 as coordinates. However, in some cases, we might be interested in the time information. For example, one might want to know the time history of the system state starting from a specific initial point. Another relevant situation is when one wants to know how long it takes for the system to move from a point to another point in a phase plane. So, practically, we must solve the equations with respect to time. So, in this case, we make this technique. We consider that delta t is approximately this, and we solve this. We take this equation, and then we take this integral. We obtain this integral from this. I think, just a minute, I think that we must finish here, and at this point we will finish the first lesson, and we will continue the next Thursday from this point, because now this point is very important, and we must report all these things that are very important. And this is the end of our lesson today. We must stop here, and then we will continue after 1 week. Thank you very much for your attention. If you have questions, please study it very well. You must study. What will you study? You must study the first 30 pages. You must study the first 30 pages. If you have questions, don't hesitate to contact me. You can contact me by email, or I will show you. I will give you my telephone. I will give you my telephone. Okay, my telephone is this. This is my telephone. I will give you also my Greek telephone. My telephone in Greece is this. And this is also, this number is also Viber and WhatsApp. So you can contact me. This is my phone. This is my phone. This is my phone, and this is my phone in Bulgaria. This is my phone in Bulgaria, and this is the second is my phone in Greece. This is my phone in Greece. Okay. So you know my email. These are my telephones and Viber and WhatsApp. So if you have questions, don't hesitate, please, to contact me. Study now the first 30 pages from this book, and we will continue next Thursday. At the end, each student, we will see, maybe we will have examinations, written examinations, or maybe I will give you to everybody, I will give you homework. We will see, and we will decide at the end. This is a very interesting course, but you must have knowledge of differential equations and automatic control. So please make a repetition of mathematics of the first 2 years, calculus of one variable, calculus of many variables, differential equations, and control systems, automatic control systems theory, because this is the necessary and sufficient background to understand the course of nonlinear systems. And the course of nonlinear system is the half of the course nonlinear systems, neural networks. So this was the end of our lecture. Thank you very much. I will upload this lecture on YouTube, and I will send you the link from the YouTube. Okay, so thank you very much for your attention. Good night. Good morning.